All right, this video we're going to take a look at the circuit analysis document here in your packet. This is a document that I wrote up, and it's for helping you take a look at when we start combining series and parallel elements in a circuit. So at first there's a little bit of review of ideas here. So running through very quickly, you would say, hey series, what series? Hey series. Anyway, series is when we go ahead and we connect items in a circuit. I like to think of it as being, in this particular way, I like to think of it as being one element and then the next element. In other words, the current has no choice of path. The charges, they'll go through one element and then the next and then the next. Then we say they're hooked up in series. Parallel, on the other hand, we say, hey, parallel is like dot, 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 or dot, 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 right? So this way or this way. So it'll go through one item or through another. So the current is going to split, and some of the current goes one way and some of it goes the other way. And so any one particular charge does not go through both items. It goes through one or the other. Then we'll say that they're in parallel with each other. So it's a choice. The current has a choice of path. And again, I'm not saying that all of the current goes one way. It's each individual charge has a choice of which path it would flow down. All right, electric potential, also called voltage. You say, hey, that is that's our V, right? Or also, yes, V. And you say, what is that? We talked about that being the UE per Q. You say, this is the potential energy per charge. And you say, this thing to keep in mind is this is a property of a location. So we don't say an object has a certain V or a charge has a certain V. That doesn't really technically make sense. It's a location, a certain spot has a certain V value. And so, like I said, we can put a flag on the ground here and say, hey, right here, the V value is this much. Okay, oftentimes we do like an analogy. We talk about gravitational potential, but again, this is per charge. All right, and then electric current. We said, hey, the electric current, that is my rate of flow of charge. And again, my units for it, you say, we think about it as being current is my rate of flow of charge. Oftentimes, in what we're doing right now, we're going to be dealing with current that's constant. Okay, until we start dealing with like charging capacitors and discharging capacitors, we're going to be dealing with flow that's constant. And so, my I bar, my average flow will just be the flow because it's constant, and that's just going to be then the amount of charge that flows by in a certain amount of time. All right, my charge per time. All right, and the units we use for that then it would be, you say, hey, in units would be like coulombs per second. Of course, we're going to have that in amps. All righty, moving on. So we say, hey, resistors. Resistors, do they add, remove, or not change the electric current flowing through them? And you say, well, we can't create or destroy charges, so whatever flows in one end is going to flow out the other. So resistors do not change the current flowing through them. Now, if you add resistors to a circuit, then that will change how much current flows through, right? Or if you remove resistors from a circuit, that'll change depending on how you add them. But I'm talking about if you got a resistor in a circuit, it itself does not change the amount of current. So current entering a resistor is equal to the current that exits the resistor. Resistors, add, remove, do not change. They remove energy from the charges going through them. As the charges try to move through the wire in the resistor, they're going to bump into impurities in the metal or discontinuities of crystal structure or whatever, and they're going to bounce off those atoms and shove on them, and that will make those atoms start to wiggle and jiggle faster. We're turning energy from the motion of the electrons into thermal energy, wiggles and jiggles of the particles in the wire, generally is what's going on. And so, yes, the resistors are removing energy from the charges flowing through. So the energy of the charges entering the resistor is greater than what comes in is greater than what goes out, right? Okay, because we lose some energy going through the resistor. Therefore, the electric potential on one side must be different than the electric potential on the other side of the resistor. Batteries, on the other hand, they thinking about it, essentially they're adding energy. A lot of times we think of a battery and like an analogy as being like a pump, like we do this, gravitational potential is an analogy for electric potential. We think about batteries essentially as being like pumps lifting the water up, kind of, giving them more potential energy. Batteries add, because you're going from one metal to another metal, inside the battery. Batteries add the energy. Well, that's weird. There's a typo. Oh my gosh, I got this grammatical error there. That's terrible. Batteries add. I guess I didn't have a good way of doing the grammar there, because you'd say they add to the energy of the charges flowing through them, or they remove from, right? Or they do not change the energy of the charge. Yeah, see, so like grammatically, like I had to have different ways to write that for the three different options. That's awkward. Anyway, so the energy of the charge is entering a battery is less than the energy of the charge is leaving the battery. Therefore, the electric potential on one side of the battery is different than the potential on the other side of the battery. So you'll have changes in V when you go through a resistor or when you go through a battery. The third thing that you'll have changes of V in is capacitors. If the capacitors are charged, you'll have a change in V from one side to the other side. I'm sorry. Yeah, yes, there'll be changes in V from one side to the other side of a capacitor. So that's the third thing we'll deal with, but not yet. Okay, let's do some calculations here. So, question 3, this is referring to this diagram here. You can see I've got 1, 2, 3 resistors, right? And I can see that my current here, right? I'm kind of skipping ahead. You see my charge is flowing in here. They'll flow in one side of the resistor, going to flow out the other side, which will then go into the next, which goes out the other side, then it goes in the next. The current has no choice of path. So these are attached in series to each other, these 3 resistors. Okay, they're giving us the values for them, 20 ohms, 40 ohms, 60 ohms. I'm just going to go ahead and label that right on the diagram. Something I'm going to tell you is that whenever I do circuit problems, right, it is best to just go ahead and write right on the diagram. 20 ohms, 40 ohms, 60 ohms. Okay, those are my 3. Those are my 3 resistances. They'd like to know, hey, what's the total resistance? Hey, when they're in series, we just add them up, don't we? You say, hey, the formula for resistance in series, it's just the sum of all the individual resistances of all the resistors. So in this case, that's going to be just 20 plus 40 plus 60. And you say, hey, that's going to be 120 ohms. If my current going into that section is 6 amps, then they ask, hey, can you find the delta V for the whole circuit piece shown? Well, you say the key idea here is in series, right? We just said before that this current that flows in the one, the current flowing through here is the same as the current that flows through here, the same as the current that flows through here. That's just 6 amps running through this whole mess, right? 6 amps the whole way. There's nowhere else for the charges to go, right? And so I'm going to kind of cheat and jump ahead and say, hey, this is going to be 6 amps, 6 amps, 6 amps. So what I'm going to do is I'm going to think of these 3 resistors as one region of the diagram. And this whole region, I've got 6 amps flowing through. I want to find the delta V, so I can do a little delta V as IR, right? Ohm's law. We're going to use Ohm's law over and over again when we do circuit problems, right? And so the whole region, the delta V, is the whole region has 6 amps going through it and has a resistance of 120. And so you say that whole delta V is going to be 6 times 120. And you say, gosh, that's just 720 volts. Okay, that's my delta V for the whole region. But now when I'm going to use delta V for this next part, when they want to know the delta V's for each individual part, you see, I can apply Ohm's law again. And I can say, oh, delta V is IR. But now I'm going to use it just going from here to here. For that first part, I had said, imagined I'd hooked up my voltmeter like this over this whole chunk, right, from start to end, right, treating it like one whole region. And that gave me 720 volts, right? But now, if I go ahead, I'm going to hook my voltmeter up just for each individual part. What's the delta V for resistor 1? And you say, well, that would be if I hooked up my voltmeter from here to here, just on either side. You say delta V is IR, my delta V is going to be 6 amps flowing through just this first resistor, 6 through 20. You say that'll be 120 volts. What about the second resistor? Hook up a voltmeter here to here, and you say, hey, my delta V, it's going to be 6 amps flowing through 40 ohms. That'll be 240 volts. And then for the third resistor, you say, I'm going to have 6 amps flowing through 60 ohms. So I hooked up my voltmeter, 6 times amps times 60 ohms would be 360 volts. And you say, hey, wait a minute. You know, my charge is flowing through. They're going to start off maybe with some high potential. Whoops. With some higher potential here as they start off. When the charges go through the resistor, they're going to dump off energy, and so their V level will drop down. Then we go through this resistor, and they'll drop off some energy, and the V level will drop down. And they go through this resistor, they drop off some more energy, and the V level drops down one more time. And we said, hey, going from purple to red is 720 volts. Well, then if I drop down purple to blue and then blue to yellow and then yellow to red, I better end up at red. I better end up having gone down 720. And if we were to go ahead and add up 120 plus 240, that's 360, plus 360 is 720 volts. That matches what we had before. Okay, so it does make sense. And so that's looking at just analyzing some resistors in series. Now we're going to go ahead and take a look at this arrangement. Now I've got 2 resistors, R1, R2. You say these charges are in parallel. You say my current comes flowing in here in the left side, but then when it gets to this junction, it has a choice. And so some of the current will go this way. We're going to call that I1, and some of the current flows this way, I2. And they have a choice of going through either resistor 1 or resistor 2. Then it's going to flow back together again. And so to get from this spot here to this spot here, right, they have a choice of going through R1 or R2, so they are officially in parallel. If I go ahead and do my color coding trick for V's, right, which I think is oftentimes helpful, then I would color code here. All of this is all one bit of conductor connected. And until I hit an object in my circuit that's going to change the V level, right? It's going to take energy in or out of charges, like a battery or a resistor or a charged capacitor. I am just going to have the same V levels. This is all purple. On the other hand, we're going to go through the resistor, drop off some energy. Our V level will be lower. My energy per charge will be lower over there. So I'm just going to tag that like this. And again, all of this is connected. And so down here, it's at some different V level. Okay, what are they asking? First, what's the total resistance for these guys if R1 is 20 ohms and R2 is 40 ohms? And so, taking a look at that, you say, let me go ahead and write that on there. You say, hey, this is 20 ohms, and this one down here is 40 ohms. And so my total resistance, say they're in parallel. So I would use the parallel formula for resistors in parallel. That's 1 over that total in parallel is going to be the sum of the reciprocals of all the individual resistances. And so in this case, I would say 1 over my R parallel is going to be 1 over 20 plus 1 over 40. You say, if I want to add that, you say, I got to get common denominators. So I'm going to multiply this one by 2 over 2, right? Yeah. And so then I'll have 2/40 and 1/40 is 3/40. But remember, that is not the answer, right? That's 1 over the answer, right? I got to, now that I have just 1 over RP equals 3 over 40, I can flip both sides and I'll get 40/3 ohms for my total resistance. Okay, so that's 13 1/3. And you say, hey, 13 and third ohms, that's smaller than either of these by themselves would have been. You say, yeah, if I just had the 20 ohm resistor, I'd have 20 ohms. But when I have this extra branch, some of the charges can get through that way. I've just made it easier for charges to get through than if there was just the one resistor to have to try to wiggle through. So they can spread out a little bit more. They're not quite as jammed together. It makes it easier for the electrons to get through. Okay, if my total current coming in is 6 amps, so that's my current coming in here, it's going to split up. They say, hey, what's delta V for this whole region? Something that I like to do on diagrams, again, I like to take my notes right on the diagram so I have the numbers there where I need them. You'll see this will be more useful as we get to bigger diagrams with more stuff. But once I find the resistance of a region of the graph, I like to write that right in on the diagram. Okay, this you'll see how valuable this is later on when we do bigger problems. But I write it right in there in a circle so that I know that I've already calculated the resistance for that region and I can use it. Because we're going to use that number right now. We want to know delta V for the whole circuit piece. So that would be if we hooked a voltmeter up and we went from one side to the other side with our voltmeter and hooked up from here to here. What's the delta V for this whole thing? So I'm going to use Ohm's law. Ohm's law, you got to know two variables to find the third. You say to find the delta V there, I'd have to know the current through that region. And you say, well, yeah, we know 6 amps is what flows through this whole bit. I mean, I get split up on the way, but 6 amps goes to this whole region. And so I'm going to put in the resistance of the whole region. So it's going to be 6 amps flowing through 40 thirds ohms. And so when I calculate that out, that's going to give me 80 volts. And so that is my delta V that would fit here for that whole region. Okay, that is actually like at the core, the trickiest part of these problems is, starting to find currents and delta V's down individual branches. And the tip is first find the resistance for the whole region and then take the whole current going into that region times that to find the delta V for that region. Because now to find the current through these individual little branches, right? You say, I'd have to use Ohm's law and I have to do delta V is IR, right? But now I'm applying it just to this little bit, just for resistor 1, right? Like I hooked a little voltmeter up here. And you say, well, that again, you say, wait, the delta V there for just this branch, purple to red, that's the same as any purple anywhere to any red. That's still just 80 volts. So I can use that delta V I just found using the resistance for the whole region now to solve for currents in just this little branch. And so if I do that, 80 volts is that current through that branch that I'm trying to find, right? All right, times the resistance of just that branch, which is 20 ohms. And so I can find that current in that top branch, that I1, is 4 amps. So that's what flows through that side. It's just 4 amps, goes this way. And again, since I found the delta V for this whole region for purple to red, again, if I did my delta V, now looking at just this bottom resistor, if I hooked up a voltmeter, that would also read, oh, look, purple to red. It's also got to be 80 volts. Okay, anywhere in purple, anywhere in red. And so I can do delta V as IR for just that bottom branch. And if I do that, I can say 80 volts is going to be I2 times the resistance of that branch, which is 40. And so you say, hey, I2 is going to end up being 2 amps. And hopefully you feel pretty good about that 2 amps. You say, yeah, because look, 6 amps flowed into this little intersection, this little junction here, right, on the left side. And so 6 amps flows into the junction. I better have 6 amps of charge going out because you can't create or destroy these little electrons, can't create or destroy charge. So if 6 goes in, 4 goes one way, 2 goes the other way, right? It has to add up to be 6. So we can use the Kirchhoff's junction law, that the current into the junction equals current out of the junction. We can use that to double check, right? And again, junction law, the sum of all the I's going in equals the sum of all the I's going out of a junction. So you can double check with the junction law and make sure that makes sense. Okay, finally, now we're going to go ahead. We're going to add in a third resistor to the same circuit we were just working with. All right. So take a look up here. You say, again, this guy was 20 ohms. This guy was 40 ohms. Now we're going to add another 20 ohm in here. All right. Now, we want us to find the total resistance. For some folks, their first gut instinct is to say, oh, look, I can see the wire splits. It's a parallel circuit, and there's 3 resistors, 20, 40, and 20. And they want to say, oh, okay, we'll use the parallel formula. And we'll say, hey, 1 over our parallel, that's going to be 1 over 20 plus 1 over 40 plus 1 over 20 for those 3 resistors. But that is incorrect, okay? Because, again, what parallel is about the current having a choice. And what I want to do is add up the inverses of the different choices. What is the choice the current has? Well, if I go ahead and do my color coding, then you say, here's my high V part. I'm going to just go ahead and highlight all of that wire, right, until I get to something that's going to take energy in or out. At the other end, I've got the low V side. Once I'm done, you say, okay, all this here, color code, all that, right? All at the same V level. But you notice there's a little in-between drop there, right? Mm-hmm. And so here's the deal. When I think about my current flowing in the circuit, my current is going to come in here. When it gets to this junction, it's going to split. Some of it goes this way. We're going to call that I1. Some of the current splits and goes this way. They call that I2. So the point is the charges have a choice of path. But what's the choice? It's not a choice between going through R1 or R2 or R3. The choice is go through R1 or go through the combination, right, of both of these. And so what's in parallel is R1 and the combination of R2 and R3. So what I need to do is I need to first find the total resistance of the lower branch of R2 and R3 together. So I'm going to do that. First saying, hey, R2 and R3, you'll notice that this current that flows to the bottom branch, what goes through R2 then is going to flow through R3. There's nowhere else for the charges to go, right? So those currents are the same. And so these are in series with each other. So first, we're going to add up the bottom branch and say, hey, 40 plus 20 in series, you just add them up. The bottom branch is going to be 60 ohms. And so what I have in parallel up here is I actually have the top branch, which is 20 ohms, and that's in parallel with the bottom branch, which is 60 ohms. So that's what I have to add. Okay, so adding these fractions, you got to get a common denominator, so I'm going to multiply this one by 3 over 3. And so when I do that, I'm going to have 3 60ths plus 1 60th is 4 60ths. Okay, but again, remember, that's not the answer. That's the inverse of the answer. I got to flip at the end. And so it'll be 60 over 4. 60 divided by 4 is 15 ohms. I'm going to put that right there in the middle on the diagram where it's useful for me so I can see that's my answer. I don't have to go scouting around through blanks. So, hey, now I want to know if I tell you the total current coming in is 6 amps. What is the delta V for the whole circuit piece? So that would be if I hooked my voltmeter up for the whole thing. So I connect somewhere here at the start, my voltmeter, and I connect here at the end. What would be the delta V I would measure? And so the trick to doing this is say, I'm going to treat this not as 3 separate resistors, but as the whole region. I'm going to analyze that whole region with Ohm's law. Delta V is IR. And delta V for the whole region, I'm going to take the current flowing through the whole region. I know it splits up to different branches. We're looking at this whole thing as one big chunk. And with the resistance for the whole thing of 15, that'll give me the delta V for that whole region. So 6 times 15, that gives you 90 volts. And so that's my delta V. From purple to red is going to be 90 volts. And I can fill that blank. That's it. So that's the trick, is treat the whole thing like one big resistor with the full current of 6 amps flowing through it. That's the trick. Hey, what's the current now in this top branch? Now that I know the delta V from purple to red, which I solved by using the whole region, now I can use that same delta V for just this branch. And so if I go ahead and do that, you say, just looking at the top branch, delta V is IR. You say, okay, my delta V, 90 volts, is going to be 6 amps through, it's going to be, delta V 90 volts is going to be that current through the top branch times the resistance of just the top branch. So I'm using to find the current through just the top branch. Make sense? So you say 90 divided by 20, that's going to give me 4.5 amps. Okay, is going to be I1. So I know that this current flowing here that goes this way, I can label that 4.5 amps. And I can fill in my blank, 4.5 amps. What's the current going through the bottom now? And you say, well, we could use Ohm's law again. We could do the same trick for this bottom branch. Again, we'd be taking a look at going from purple, just look at the bottom branch, so from purple to red. And you say, well, look, the delta V here, that's just purple to red. I already know that for the bottom branch, the same as the top branch, is going to be 90 volts. And doing delta V as IR this time for the bottom branch, I'm going to have 90 volts is my current through the bottom, I2, that I'm trying to find, times the resistance to the bottom. That whole bottom branch had a resistance of 60. 90 divided by 60, that's going to give me 1.5 amps for I2. And you say, well, that should make logical sense to you, because if I use the junction law here and I say the current flowing into this left junction has to equal the sum of the currents going out, you say, well, 6 is equal to 4.5 plus 1.5 amps. So that double checks, and that makes logical sense. All right. What's the delta V across R2? Now I want to know something different. You say, now I want to know the delta V just in this part. Okay, and say, well, this delta V better end up being less than the full 90 volts to go from purple to red. It's going to be a step down, part way down, and then the rest. So you say, now I want to do the delta V is IR just for this little resistor, just for R2 by itself. And so if I did that just for R2, delta V is IR. This time, the delta V is what I'm trying to find. The current through that bottom branch we just found was 1.5 amps. And the resistance for just that first resistor is 40 ohms. And so you say, that's a 4. And so you say 1.5 times 40, that would be 60 volts. And so the delta V here is 60 volts. Hey, what's the delta V have to be from green to red? The whole thing from purple to red is 90. Here's 60. This must be 30, right? All my delta V's add up here, right, in series. And you say if I double checked using Ohm's law, I could, delta V is IR. And so you say, hey, going down 30 volts, does that jive? 1.5 amps going through 20 ohms. And you say, yep, 1.5 times 20, that does give me 30. So that makes logical sense. So 60 volts and 30 volts. Okay, that adds up to be the 90. If someone asks me, hey, what's the power rating for this circuit? You say, well, I can calculate power 3 different ways, right? You say one way of calculating power, like the first way we wrote the formula in class was we derived it as I times delta V. But we could use Ohm's law to make substitutions. Since delta V is I times R, this would be I times R. So we could write power as I squared R. Or we could, using Ohm's law, rearranging delta V as IR, we could say my I is delta V over R, and substitute that in for I, and I'd have delta V over R times delta V. Or if you like, delta V squared over R. So that's which way is going to be easiest for us. And we can solve. Since we solved for all of our currents and all of our delta V's and all our resistances, we can solve for the power any way we want. I'm just going to do what looks the easiest to me in this case. So for the whole circuit, let's just use the first one, I delta V. You say, hey, we figured out already. We know we were given that the total current through the circuit was 6 amps, and we know that the delta V, we calculated it to be 90 volts. And you say 6 times 90, that would be 540 volts. I'm sorry, this is power, right? Sorry, 6 times 90, 540. But the units are going to be what? Watts, right? Remember the energy per second, that's what this power rating is in watts. So every second that charge is flowing through this circuit, we are converting 540 joules of energy from electric potential energy of the charges into probably thermal energy. I mean, maybe some of these are light bulbs and some of the energy is going in the form of light, but we're taking energy out of those charges at that rate. If there was a battery hooked up that's powering the circuit, every second we're taking 540 joules of energy that was stored up chemically, right, in those different materials, those two, in the arrangements of those electrons and protons and those atoms of the two different electrodes of that battery, and we're slowly rearranging them, right, and changing that electric potential energy, if you like, chemical potential energy, and converting it into thermal in this circuit, and that's what's going on. Okay, now they ask us about what's the power for just resistor 1. We're just resistor 1, you'll say, well, we know the delta V is 90, and the current going through is 4.5. So I times delta V, 4.5 times 90. Can we do that one in our heads? Sure. 4 times 90 is 360. Half of 90 is 45. So 360 plus 45 would be 405 watts. I didn't make that blank very big. And you say, what about R2 here? You say, R2, we had a current of 1.5 amps going through a delta V of 60 volts. So I would just say, again, using I times delta V, 1.5 amps times 60 volts, that's going to be 90 watts. And you say, what about R3? R3, we have a current of 1.5 amps going through delta V of 30 volts, 1.5 times 30, that would be 45 watts. And you say, hey, that's all the resistors in that area of the circuit. You say, well, hey, if I add it up, how quickly all of them are taking energy out of the charges. 405 plus 90 would be 495. 495 plus 45 would be 540 watts. It makes sense. It matches up. And so that's it. So to me, the tricky part here, just to reiterate, for me, I think the tricky part of these circuit problems is finding like currents and delta V's in a little branch, okay, of a parallel part like this. And so the trick is, first, find the resistance of that whole chunk, right? And I write it down and put in a circle in the middle. And then take the total current times the total resistance to find the delta V for that whole chunk. Because once you find delta V for that whole region, I can apply that delta V for each branch. And now I can find the delta V for the branch times the resistance of the branch to get the current through the branch. You know what I mean? Delta V divided by R for each branch to find the current through each branch. And that's like the trick, is to first treat it like the whole region as one big equivalent resistor with the full current through to find the delta V for the whole branch. That really helps. All right. I think that's going to do it for this video. Next video, we'll be taking a look at these 3 circuit problems and walking through them very quickly.